Hello everyone and welcome back to my channel Gyan Sampada. In our previous class we had a discussion on the details about antiferromagnetism as well as we had an introduction to the model which explains about the property of antiferromagnetic material. And today we are going to continue with the same in detail where we are going to discuss about molecular field theory of antiferromagnetism. So while we were studying about ferromagnetism also we dealt with the molecular field theory relating to ferromagnetism, and today we are going to understand some details about molecular field theory of antiferromagnetism. So the relations what we have seen in ferromagnetism, similar relations will be carried on in antiferromagnetism also. So if you have not gone through that class where we discussed about molecular field theory of ferromagnetism, then do check it out in the playlist section of ferromagnetism. So let's start our today's class on this topic. So whatever we are going to study under this heading is to explain the behavior of antiferromagnetic material, and the model which is used to explain the properties of antiferromagnetic material is called as the two sub lattice model. Introduction was taken up in the previous class also, and today based on that we will build up our further knowledge. So two sublattice model. Clearly we can say that there are two separate sublattices which form a total model which helps us in explaining antiferromagnetism. So if you consider a lattice system in which the magnetic atoms are arranged in BCC structure, that is, we can observe it in this unit cell diagram where atoms are present at the corners as well as there is one atom at the body center which is shown with a red mark. In this two sublattice model we are going to visualize all ions at the corners are having spin up, whereas all the body centered atoms are having the spin down direction. So this simple case of magnetic structure is with two interpenetrating simple cubic sublattices such that the spin moment of atoms in one sublattice array are antiparallel with the spin moments of the atoms in another sublattice array. That is, blue atoms at the corners corresponds to one sublattice which are having spin up, whereas the red atom, when you reproduce the whole system in all the three directions, then we can observe that the body centered atom are having spins in downward direction. So clearly the feature of antiferromagnetic material is shown here, where we have seen that antiferromagnetic materials means their moments are equal and antiparallel to each other. So here atom A and atom B are antiparallel to each other, which means that the model corresponds to antiferromagnetic nature. So we can say that the body centered atom is atom A and the cornered atoms are atom B, or vice versa. Both the way can be taken up. Even we can consider spin up for the body centered atom and spin down for the corner atoms. So if we consider the temperature dependence at absolute 0, that is 0 Kelvin, the spin moments of both the sublattices, that is sublattice A and sublattice B arrays, are ordered. Means they are perfectly antiparallel to each other. So if we consider the net magnetization, then it is going to be 0 because of the mutual compensation, because the net effect coming from the spin up will be equal to the net effect coming from the spin down, and as their directions are opposite to each other and they are equal, they are going to cancel out. That is called as your mutual compensation, which leads to 0 net magnetization. But this is at absolute 0. But what happens if temperature changes? As the temperature increases or as the temperature is raised, the antiparallel arrangement of spins is gradually disturbed. So whenever spins are not exactly antiparallel to each other, their net magnetization will not be equal to 0. So as the temperature increases, The spin arrangement is disturbed, due to which the magnetization rises and it becomes maximum at certain temperature called as Néel temperature, which corresponds to Néel point, and above this temperature the material behaves like a paramagnetic material. So below Tn we observe antiferromagnetism and above Tn we observe paramagnetism. So this is a brief introduction to this molecular field theory. Now let us understand some details based on the equations. Here we have considered that atoms A have only atom B as the nearest neighbors and atom B has nearest neighbor as atom A. So next higher neighbors we are not going to consider. And when we are considering the nearest neighbor interaction, we can define the internal field on atom A or A ions as HA is equals to H minus lambda into MB, and internal field for B ions HB will be equal to H minus lambda MA, and here lambda is nothing but the internal field constant or what we had seen as V's constant. And here we can observe that HA, which is the internal field on A, is due to the atom B, which is the nearest neighbor. So magnetization in B is going to affect the internal field of A. Similarly for the B ion. So we can say that the set of equation number 1, first part explains the interaction of A over B and second part explains the interaction of B over A. That's why HA has MB and HB has MA. And this internal field constant is going to determine the strength of exchange interaction. So this in detail about this equation and V's constant, internal field or exchange field, everything is already discussed while discussing ferromagnetism. So now we are just going to move to the next part. So roughly we have seen what happens at T is equals to 0 Kelvin, that is net magnetization is 0, and as the temperature increases magnetization is going to rise and finally it will become maximum at Néel point or Néel temperature. So here we can divide the whole thing in different cases. So case 1 will be temperature greater than Tn, that is Néel temperature, and similarly case 2 will be temperature less than Néel temperature. So this is the case above Néel temperature, that is far away from the saturation, which occurs at T is equals to 0 Kelvin. And in order to solve this, we are taking use of the quantum theory of paramagnetism, through which we have the equation for magnetization as m is equals to Ng mu b tan hyperbolic of x. So all these notations are having their standard meaning, and we know that x is nothing but g mu b into b by kt and b can be written as mu naught into h. So simply we have substituted that, and as such it is a general equation, but we need to understand what happens with respect to the sublattices. So the magnetization of lattice A and B or the sublattice will be Ma is equals to Ng mu b tan hyperbolic of g mu b mu naught by kt remains as it is. Instead of h we are having Ha and Hb, and in place of Ha we have substituted H minus lambda Mb from equation number 1. Similarly Mb will be having Hb here, where we have substituted H minus lambda Ma, that is again from equation number 1. And let us call it as set of equation number 2, which gives the magnetization of the two sublattices. And in order to solve it further, we can use the approximation, that is tan hyperbolic of x is approximately equal to x at high temperature. Why we need to consider high temperature? Because we are dealing with the case where temperature is greater than Néel temperature. So it is already high temperature. So for that case, when temperature is high, tan hyperbolic of x is going to be approximately equal to x itself, because x is very much less than 1. So equation number 2 is reduced something like this. So g mu b into g mu b, it will be whole square mu naught divided by kt into this part as it is. Similarly, mb will be equal to n g mu b whole square into mu naught by kt into h minus lambda ma. Let us call it as set of equation number 3. So these are the magnetization for separate A and B lattices. But if we need the total magnetization, then we just need to sum these two magnetizations. That is, Ma plus Mb will give us M, which will be equal to n into g mu b whole square into mu naught by kt is constant. And when you add this, it is 2h minus of lambda into Ma plus Mb, and Ma plus Mb is nothing but M itself. So let the total magnetization equation be equation number 4. And we know that whenever we discuss about magnetism, the main thing which we are going to deal is the susceptibility. So now we are going to assume that magnetization and magnetic field which is applied are parallel to each other, and then the susceptibility is going to be scalar. So chi, which is nothing but m by h, will be equal to n g mu b whole square into mu naught by kt into 2h minus lambda m is nothing but the total magnetization divided by h. And when we simplify it by considering n g mu b whole square into mu naught by k as c, which is the Curie constant, we get chi is equals to c by t into 2 minus lambda m by h, because here 2h by h is 2 minus lambda by h into m is written here. So again m by h is susceptibility chi. Simplifying for chi by rearranging, that is multiplying the brackets, we get 2c by t minus lambda c chi by t. Then taking the second term in the RHS to LHS and simplifying for chi, we get chi is equals to 2c by t into t by t plus c lambda, because here we have taken the LCM, that will be LCM is t, numerator will be t plus c lambda, and this multiplication is taken to RHS side, so it will become division. That's why we have just reversed it and written as t by t plus c lambda. Clearly t is going to cancel out, and we write that c into lambda as Tn, which is nothing but the Néel temperature. Let us call it as equation number 5, and this is the equation of susceptibility above Néel temperature. So if you remember what we had studied in molecular field theory of ferromagnetism, we can say that there is slight difference between the susceptibilities above critical temperature. That is, for ferromagnetic material we had chi is equals to c by t minus tc, and here instead of c we are having 2c, that is Curie constant is twice, because the constant of individual A or B lattice is considered here. So we can say 1c corresponds to sublattice A, 1c corresponds to sublattice B, and instead of t minus tc we are having t plus tn. So just for understanding, let us plot a graph of 1 by chi versus t, and for a paramagnetic material we know that chi is equals to c by t, that is the Curie law. So we get the nature of graph something like this, that is the graph starts from the origin and goes on increasing linearly. And if we plot a graph for ferromagnetic material, that is according to this equation, chi is equals to c by t minus tc. This is the nature of graph, and according to equation number 5, for antiferromagnetic material we observe this nature. So this dotted line is extrapolated so that we get the intercept value as minus theta. So as that is minus theta, we observe here plus Tn. Theta is something like Tn itself, but with slight variations. And if we plot a graph of chi as a function of temperature for paramagnetic material, that is according to Curie law, and similarly for ferromagnetic material the nature is something like this, where below Tc there is ferromagnetism and above Tc it acts as paramagnet. And similarly for antiferromagnetic material also, above Tn we observe Curie's law is valid, whereas below Tn antiferromagnetic nature is observed. So these graphs are according to equation number 5 and what corresponds to paramagnetic material and ferromagnetic material. So this is above Tn. But whether there is a spontaneous magnetization above Tn or no is the question. Because according to the nature we have observed paramagnetic nature, but we need to check whether spontaneous magnetization still exists above Tn or no. And we know that spontaneous magnetization is nothing but the magnetization even in the absence of external magnetic field. So here we will consider H is equals to 0, that is external magnetic field is not applied. And already we have seen the magnetization value of sublattice A in equation number 3, I guess. Ma is equals to n g mu b whole square mu naught by kt into h minus lambda mb. And here we are going to put h is equals to 0 and rearrange the equation by considering n mu naught g mu b whole square by k as c and getting a equation ma plus c lambda by t mb is equals to 0. Similarly, we will do with the sublattice 2, that is containing atom B, putting h equal to 0, putting the c value and rearranging the equation. So this is set of equation number 6, and for t greater than Tn, equation number 6 have its trivial solution, that is Ma equal to Mb equal to 0. That is, if you solve it here directly, you can observe that both the values are going to vanish, which means that there is no spontaneous magnetization of the two sublattices above Néel temperature. So clearly we can say that above Néel temperature there is no spontaneous magnetization. So there is a randomness in spins, that's why we call it as paramagnet above Tn. And if the spontaneous magnetization of sublattices is supposed to set at T is equals to Tn, then equation number 6 must have non-trivial solutions for Ma and Mb, that is at that temperature. And if the solution has to be non-trivial, then the determinant of equation number 6 should vanish. That is, for finite magnetization, we can just solve this determinant. So the coefficient of Ma is 1, Mb is c lambda by t. So this is according to equation 6a and this is according to 6b. When we solve it, that is 1 into 1 is 1 square minus c lambda by Tn whole square. That will be c lambda by Tn whole square equals to 1. And when we solve it, square root of 1 is again 1 itself. So c lambda will be equal to Tn. And that's why we had considered in the previous slide c lambda is equals to Tn itself. And now theoretically also it is confirmed. So when you compare it with the ferromagnetic material, Néel temperature looks same as paramagnetic Curie temperature Tc. But when experimentally checked out, Néel temperature Tn is generally less than that of Tc, that is Curie temperature. Because this two sublattice model is oversimplified and it is not the actual case, and the actual situation is more complicated than this. That's why theoretical readings are something and experimentally there is some discrepancy in the readings. So this was case 1, that is what happens above Tn and at Tn. Case 2 of this part, where we are going to deal with temperature less than Néel temperature will be taken up in our next class, which will be the continuation of today's class. So see you in our next class. Till then, study well, practice more, and thank you for watching.